So, hello everyone again. This is lecture number 4 for the chapter Work, Energy and Power. The last discussion which we have concluded in the previous lecture 3 was based upon understanding the concept of variable force in work. So, the basic crux was that what is work done? Work done is basically the area under the curve for a graph between f and x. Okay. So that thing being said, today we will start a new discussion. So let's start a discussion directly. So I'm Samir Lawankar. This is lecture number 4, and the chapter name is Work, Energy and Power. So let's begin our discussion. So currently we are on the 6th topic, that is the work energy theorem for a variable force. Okay. So we have completed with the introduction. We have completed with the notions of work and kinetic energy. That is the work energy theorem. We have completed the work, understanding of work. We understood kinetic energy, and in the previous lecture we have understood the work done by the variable force also. Okay, now let us understand the work energy theorem for the variable force, and then we can move forward to understand another term which is called as the potential energy. We will understand what is this potential energy. These two are the basic building blocks of your complete work and energy concept. The first was kinetic energy, the second is potential energy. Fine. So that thing being said, let us first understand the work energy theorem for the variable force, and then we can move forward to understand the concept of potential energy. So let's start the work energy theorem for a variable force. Let's start this subtopic, which is the work energy theorem for a variable force. So just a quick revision about the work energy theorem. What is the work energy theorem? In mathematical form, the work energy theorem states that the change in kinetic energy is nothing but equal to the work done. Correct? So what was the previous discussion which we were supposing that assuming the force is constant, what do we say? That let us assume that this is a mass m which is moving with the velocity v, or let us say the initial velocity is u. It covers this much amount of displacement due to a force which is acted upon, which was F, and finally it reached here, and after finally reaching here, it has a velocity v. Then what we can say that the change in the kinetic energy, that is final minus initial, it's half mv square minus half mu square is nothing but equal to a scalar product of f and d. In this case scenario, it can be written as nothing but f multiplied by d into cos of 0 degrees. As cos 0 is 1, we can write this as equal to f multiplied by d directly. Only this case scenario because f and d are in the same direction. Fine. So that being said, this was simple kinetic work energy theorem. Now let us understand the work energy theorem for a variable force. So we are now familiar with the concepts of work and kinetic energy to prove the work energy theorem for a variable force. We confine ourselves to one dimension to increase the simplicity so that there is no complexity involved in the future discussions. Let us first understand this complete concept for one dimension only. Okay. So first of all, the time rate of change of kinetic energy. Let us first calculate the time rate of change of kinetic energy. So what is K basically? We know K is nothing but equal to half m v square. Correct? So dk by dt, let us try to calculate dk by dt, that is time rate of change. So this is what? It is time rate of change of kinetic energy. Okay, so it's time rate of change of kinetic energy. So it is nothing but d by dt of kinetic energy, that is nothing but half m v square. Okay. Now look at here very carefully. Okay, so here what we can say, we can write this as nothing but equal to we know that kinetic energy or change in kinetic energy is also equal to force into displacement. Correct? Force into displacement using the basic concepts of your kinetic energy theorem. Okay, in differential form, what we can write this as equal to? We can write this as equal to f into dx. Correct? Now we are just trying to understand how did this thing has arrived. So This is to understand in very differential form, but we just need to understand how is this thing arriving, or how is this thing being derived. Okay, so dk by dt is nothing but equal to d by dt into half mv square. Okay, now we know that mass is a constant, 1 by 2 is a constant. This v square is not a constant, it's a variable which depends on time, correct? So what we can do, we can just take out half m from here and we can do d by dt of v square, correct? So d by dt of v square will give us half m into 2v into dv by dt. Okay, so this is how the differentiation of a variable, which is itself a function of the differential coefficient with which whose respect a differential is being performed, is done. So just explaining it again here. So let us say we need to do d by dx of some quantity v to the power n, let us suppose. So this is nothing but equal to n into v to the power n minus 1 into dv by dt again. So that is how we can understand. This will be much more clear when you will understand the concept of differentiation in the mathematics. So generally physics takes into consideration that you know these terms, but I am just revising the basic terminologies which are being used here. Okay, so it's a simple rule, there is nothing, so a simple concept called as chain rule is being involved here, and we just did this simple calculation. Okay, fine. So we got it is equal to nothing but half m into 2v into dv by dt. Okay, now so here 2 gets cancelled. So what we got is m into v into dv by dt. Okay, now if you see this clearly, what is this? dv by dt, that is change in velocity with respect to time, or rate of change of velocity with respect to time. If you remember correctly from the chapters of motion in a straight line, motion in a plane, this is nothing but your acceleration, correct? So change in velocity with respect to time is nothing but your acceleration. Okay, so I can write either directly this is acceleration, or I can write it as m dv by dt, m dv by dt into velocity. Now if you remember or you see this thing clearly, it is nothing but mass into acceleration, which is nothing but force, which you understood in the chapter of laws of motion, correct? So therefore you can write dk by dt is nothing but equal to force into velocity. Okay, now what is velocity basically? Velocity in differential form can be written as nothing but f into dx by dt, correct? So now we can directly because these are very different in differential forms. So in differential forms, as it is dt on both sides, so we can remove or segregate dt, and therefore what we are left with, we are just left with dk is nothing but equal to f dot dx. So dk is nothing but equal to f dot dx. Okay, so what can be understood from this? That the small infinitesimal change in the value of the kinetic energy is equal to force multiplied by infinitesimal change in x. But there's a catch here. Let us see the catch here. So dk is nothing but equal to f dot dx. So I hope it is clear how we derived or how we arrived at the situation. We went into starting with dk by dt. We went into understanding that this is nothing but m dv by dt into v. And we wrote this as force. We changed value of velocity into dx by dt. We removed dt from both these sequences and finally arrived dk is nothing but equal to f dot dx. Now dk is nothing but equal to f dot dx, but please remember that if we are integrating or if we are multiplying or we are adding this dk terms again and again, this f here is a variable, correct? So this f may change or will be integrated depending upon how this value of f or the function f holds. Okay, so if it's a function of x, then that value of x will be integrated in terms of its rules, which are the integration rules. Okay, so everything which I'm just uttering will be explained much more clearly when we will do some of the examples related to it. Okay, so dk is nothing but equal to f dot dx, not f dot dx, f dx. Okay, so now let us integrate it. So when we integrate it, it's nothing but integration of dA into integration of f dot dx. Okay, so the limit of the integrals are always depending on the differential form. On the left hand, as it is the differential of dk, it will start with ki and at kf. Similarly, what will be the x value? X, as for ki, the value of initial displacement is xi, and the final displacement is x. So that is how we denote it. Fine. This integration will be simply kf minus ki because there is nothing else here. So it's nothing but integration of 1, which is the same value which is k. Putting the limit, we'll get kf minus ki. And this is nothing but equal to integration xi to xf f dx. Correct? Now let us look at this equation very carefully. If f is constant, if f is a constant, then this f can come out and this would have become kf minus ki is nothing but equal to f into integration xi to xf dx, which is nothing but equal to f into xf minus xi, which is same as f delta x, which is same as the previous scenario which we understood for the kinetic energy theorem. But this time this is not the case. We are understanding this complete concept when f is not a constant. Okay, so let us move forward here. So where kf and where ki and kf are the initial and the final kinetic energy corresponding to xi and xf. So this change to xf minus xi is nothing but equal to integration of f dot dx from xi to x. Okay. So from the previous equation, what we got, what was the work done? Work done was basically integration xi to xf fx dx. So therefore, what we can say that this work done is nothing but equal to kf minus ki. Okay, simple analogy part, nothing very difficult here. So what we basically get, that is work done is nothing but equal to kf minus ki, which is also equal to integration xi to xf f dx. Thus, the work energy theorem is proved for a variable. Therefore, here also we finally arrive at a situation in which we can understand that work energy theorem is here a variable force. Okay. So while the work energy theorem is useful in a variety of problems, it does not in general incorporate the complete dynamical information Newton's second law. So what does this line explain to you? It basically says, well, first of all, let me iterate so that everything which is written here will be usage in understanding that line. So it is an integral form of Newton's second law. Okay, why it is said as integral form? Because some sort of f dot dx has been integrated. Okay, so f value is being integrated. Okay, and with respect to x. So Newton's second law is a relation between acceleration and force at any instant of time. So what is this basically? It is nothing but f is equal to nothing but mass into acceleration. So it's a relation between mass and acceleration at any value of time, at any instant of time. Work energy theorem involves an integral over an interval of time. So during an interval, there would have been a displacement from xi to xf, and that thing has been explained. Correct? In this sense, the temporal information contained in the statement of Newton's second law is integrated over and not available explicitly. So it is basically saying that, as we know that what is the actual thing being explained here, it's nothing but kf minus ki, which is equal to integration of xi to xf f dot dx. Okay, so here nothing of sort of time is being explained. So there is no relation of kinetic energy directly involved with time. We are just integrating xi and xf, and that is only been explained here because initially what the Newton's second law was being made, it was a relation between force and acceleration with respect to time. But here when we have integrated it once, there was no usage of time directly. So that is the only thing which this line tries to explain to you, that there is no direct implicit relationship between kinetic energy and time. So in this sense, the temporal information contained in the statement of Newton's second law is integrated over and is not available explicitly. So it is not available explicitly. Another observation is that Newton's second law for 2 or 3 dimensions is in vector form. Okay, whereas the work energy theorem is in scalar form. Again, we can see a difference between the Newton's second law and the work energy theorem being explained. Okay, so those are vectors. F is equal to m into acceleration is a vector, but this work energy theorem is not a vector. Okay, so in the scalar form, information with respect to directions contained in Newton's second law is not present. So as you can see clearly that Newton's second law in 2 and 3 dimensions was in vector form. So if it was in vector form, it had a magnitude also, it had a direction also. But work energy theorem is a scalar, so it only has a magnitude. Right? So you can see clearly that when you do an integral of something which was having a vector component into it, finally you arrived at a situation which is just a scalar component. Okay, so somewhere or the other, this direction, this power of direction of this force is being hiding somewhere. We cannot actually find the direction, or there is no use of direction finding out the work done. So in the scalar form, information with respect to directions contained in Newton's second law is not present. So that information not present. We try to find out this, or when we use this work energy theory. So that is the only basic reason, or that is a basic explanation what is being explained. Because this explanation has been done in the subsequent lines. Okay. So that thing being said, we have understood this complete understanding of work energy of a variable force. Now let us move forward and solve this using an example. Okay. Fine. So please look at this example. This may involve some sort of your integration and differentiation concepts. I will try to understand, make you explain those basic rules. Otherwise, it's just simple mathematics. Okay. Fine. So let us understand. So a block of mass m is equal to 1 kg. So there's a block of mass m. Mass m is given to you as 1 kg. It is moving on a horizontal surface. So let us say this is the horizontal surface here. So let us say this is the horizontal surface on which it is moving. So it is given that the initial value of the velocity is vi, it is given to you as 2 meters per second. Enters a rough patch. So it basically, let us say this is a rough patch. It is going to enter at this location. Okay. So it enters a rough patch here, ranging from x is equal to 0.1 to x is equal to 2.1 meters. So let us say the displacement from here onwards will be starting from 0.10 meters, and here it will end at 2.01 meters. Okay. What is the retarding force? The retarding force on the block in this range is inversely proportional to x. How? It is inversely proportional like this. So for x lying between 0.1 to 2.01, the value is minus k by x, and there is no force acting when either you are towards this side or either towards this side. I hope the question is clear to you. So only and only work done which will be due to this retarding force. Okay. So where k is nothing but equal to 0.5 joules. The question asked is nothing but what is the final kinetic energy and the speed vf of the block as it approaches this patch. Okay. So let us apply the simple work energy theorem concept and solve this question. Okay. So we know that final kinetic energy minus initial kinetic energy is nothing but equal to change in the, or not change in, basically it is nothing but the integration of f dot dx from xi to xn. As another value of retarding forces are not given, we will just take the range from 0.1 to 2.0. Okay. So what is kf? We need to find it out. So kf will be nothing but equal to ki plus integration of xi to xf f dot dx. Okay. So before calculating this integral, let us first calculate the value of ki and move forward. This value of ki is nothing but equal to half into mass. What is mass? It's 1 into 2 square. Correct? So 2 getting cancelled. This is nothing but 2 joules. So we got the initial value of kinetic energy is equal to 2 joules. Now let us calculate this integration here. Okay. So what is the integration to be calculated? It is nothing but integration of 0.1 to 2.01, right? Minus 0.5, 0.1 to 2.01 into 1 by x dx. Okay. Now I'm just telling you a simple rule. So So now I'm just telling a simple rule. A simple rule states that the integration of 1 by x dx is equal to ln x, ln mod x. Okay. If I have some relation of displacements given to you, so I will put xi to xf here. So if I put xi to xf, it is nothing but ln mod xf minus ln mod xi. Now there is one more rule which we will learn in logarithms, that is ln of b, basically ln b minus ln a is nothing but equal to ln b by a. Okay, so this is another rule which you will understand in mathematics. So these are nothing but all the rules, all these concepts are mathematical concepts. I'm just making you understand those rules which are regarding your physics concept, which are important to physics. Okay, so therefore you can write this as nothing but ln mod xf upon xi. Okay, so that is the final relation here, that is it is nothing but equal to ln mod xf upon xi. Therefore, now using the simple relation, I can write this integral to be equal to minus 0.5 into ln mod 2.01 upon 0.1. Fine. That thing being said, when you will calculate this value, you will get this to be equal to minus 1.5. Okay, so you have this integral value also, 1 minus 1.5 joules. So you have this integral value also, and you calculate the kinetic energy value to be equal to 2 joules. Then what is the final kinetic energy? Final kinetic energy is nothing but equal to 2 minus 1.5, which is nothing but equal to 0.5 joules. And that is the first part of this question, in which we need to calculate the kinetic energy of the block as it crosses this patch. Now the second question which is asked is, we need to calculate the final velocity or final speed of the block. Okay, now it's a simple question. You just need to use the kinetic energy formula. So what is kinetic energy formula? It is nothing but equal to half m vf square. Just put the values here. It's nothing but half into mass into vf square. Correct? So therefore vf is nothing but equal to root over 0.5 into 2 by 1. So Vf is nothing but equal to under root 1, which is nothing but equal to 1 meter per second. Okay, so that is how you can calculate the value of initial velocity was your 2 meter per second, and then it drops down to 1 meter per second because there was a reduction in the value of, or basically because a retarding force was being applied. So that's why there was a decrease in the value of kinetic energy, and hence we can say that there is a and hence we can say that the value of the velocity observed will be less than the initial. Okay, fine. That thing being said, only a small note so that you should understand the difference between log and ln. So here note that ln is a symbol for the natural logarithm to the base e. Okay, you will understand this concept in mathematics much more clearly, and not a logarithm to the base x, base 10. Okay, so basically what is ln 10? ln x is basically log base e of x. You can just, there's a multiplying factor, it is 2.303 if you need to convert this with a base 10. Okay, so it's a simple note, so that whenever you do integration of 1 by x dx, it is not equal to your log x. Okay, so just refer to this, it is equal to ln. Okay, so that is a simple note which I just need to refer to you. So moving on, this is the ending of this subtopic, which was based upon understanding the work energy theorem for a variable force. Okay. So that thing being said, that thing being completed, now let us understand a new subtopic which is called as potential energy. Okay. So before this, we have understood something which is called as your kinetic energy. Now we will understand another type of energy which is called as potential energy. Okay. So let's start this subtopic, that is the concept of potential energy. Okay. So the word potential suggests possibility or capacity for action. Quite evident, but this is just the English meaning being explained here. So what is the word potential suggest or tells us about? It tells a possibility or the capacity for action. Fine. The term potential energy brings to one's mind stored energy. Okay, so basically, potential energy means if, let us say, this is some particle, or let us say this is some electron. Okay, so this electron will have some fine energy so that it can excite, or it can go from one place to another, right? So what we say that it has much more energy. So that energy is basically explained in terms of potential energy. Okay, so the energy which a body has, or a body has the capacity to hold it, is basically called as potential energy. The term potential energy brings to one's mind stored energy. A stressed bowstring possesses potential energy. Okay, so here is the examples to explain you potential energy. So when it is released, the arrow flies off at a great speed. Next example is the Earth's crust is not uniform but has discontinuities and dislocations that are called as fault lines. If you see clearly, so this is one of the peculiar example of a Earth's distribution. So you can see that the outermost layer is called as crust, then it's mantle, then it's outer core, and then it's inner core. Okay, so we are only and only understanding here the core concept, that is the outermost concept, that is the crust. So what happens in the outermost layer? Basically, the outermost layer of the Earth is not uniform. It has discontinuities and dislocation that are called fault lines. So these you can see are basically these blue color ones are nothing but the fault lines. So these are nothing but discontinuities which are generally observed or are actually present in our Earth. Okay. So these fault lines in the Earth's crust are like compressed springs. So basically, let us say if this is a spring, and this is an open spring, if I compress it, it will be some sort of this, correct? So what we say that it has some potential, or it has some stored energy. So it has some potential energy stored in it. So if it has some potential energy stored in it, and we are comparing the same thing with this fault lines, what we can say that these are nothing but compressed spring. That means it is having some energy injected upon it, or it is having some energy inside it. Okay, so these fault lines in the Earth's crust are like compressed springs. They possess a large amount of potential energy. Okay, so they possess a large amount of potential energy. We will understand it mathematically also. First, we are trying to understand it more visually or more in the physics terms. So an earthquake results when the fault lines readjust. So when it basically dislocates, or let us say it tries to go above one another, or it releases some sort of energy here, then due to the dislocations, or the what we can say difference in the position of the fault lines lead to the production of one of the disaster which is called as earthquake. Okay, so an earthquake results when these fault lines readjust. Thus the potential energy is the stored energy by virtue of the position or the configuration of a body. Very important line. So we understood the same definition for the kinetic energy also. So what was kinetic energy? Kinetic energy is the energy which is being shown by a particle moving with some velocity by virtue of its motion. So that was by virtue of its motion. It is by virtue of the position or configuration of a body. I will just write it also here. The kinetic energy possesses by virtue of its motion, and potential energy is basically regarding by virtue of position or configuration of body. Okay, so I hope the difference between kinetic energy and potential energy in terms of definition is clear. Okay, so thus the definition is the potential energy is the stored energy. It is the stored energy by virtue of the position or the configuration of the body. So what is the general configuration? So basically, let us say if I'm talking about a spring, so the spring is completely released, or basically it is compressed. Okay, so that is how we can understand the concept of potential energy. Okay, fine. So let's understand more about. Let's go with the further discussions regarding this topic. The body left to itself releases the stored energy in the form of kinetic energy. So what is the basic meaning? Let us suppose you have a car. Generally toy cars have some spring attached to it, so that when we rush this when we rush this backwards, so there is some sort of potential energy which starts to store in this toy cars. Okay, and then when we release it from that location, it goes forward with a very high velocity. Correct. So you or everyone may have seen toy cars in their homes or in their early childhood. Then when you try to push it towards backward, we are just what we are saying. We are storing potential energy inside. So the first step is basically storing of potential energy, and after this potential energy is stored, in the second phase, what is happening? It is being converted into kinetic energy. Okay, so that is one of the example which we can understand from this. So as you can see, the body left to itself. So if it is left to itself, if we are not applying any force, releases the stored energy. So how it is releasing the stored energy? It is releasing the stored energy in the form of kinetic energy. Okay, so I hope this example makes it clear of how there is a conversion between the potential energy to a kinetic energy. Fine. Now let us make our notion of potential energy more concrete. Let us try to understand more about this potential energy. The gravitational force on a ball of mass m is mg. Quite evident. Let us say this is a ball. It is having a mass m. Then from its center of mass, the force which will be acting out is nothing but mg. Okay, the gravitational force on the ball of mass m is mg. Here, g may be treated as a constant near the earth. So what can be understood as g here? G can be understood as, so here g may be treated as a constant near the earth surface. So this line simply means, so you will understand more about this concept in the chapter of gravitation, that g also varies, but if the height of variation or if the height of this movement of this ball is very small as compared to the radius of the earth, then the value of the g can be taken as constant. So g may be treated as a constant near the earth surface. By near, we imply that the height h of the ball above the earth's surface is very small compared to earth's radius re. Okay, so that we can ignore the variation of g near the earth's surface. Okay, so the amount of variation is very small, only and only if h is very less than. That was a simple discussion. We are talking about potential energy here. So in what follows, we have taken the upward direction to be positive. So generally, what is our sign convention? The upward direction is taken as positive, and the downward direction is taken as negative. Correct? So in what follows, we have taken the upward direction to be positive. Now let us raise the ball up to a height h. So we kept this ball and we raised this at some height h. Correct? Now the work done by the external agency. Look at this line very carefully. The work done by the work done by the external agency against the gravitational force is mgh. Okay, so what is basically happening? The ball is being kept at this location here correctly. Now what is happening? There is some force which is acting here, which is trying to pull it down. But because it is being kept at that location, let us say it is kept at some cliff here. So what is happening actually is there is some external, there would have been a force, a pseudo force which is not even visible, which is trying to keep it at this location. Okay, so that is only been explained here as external agency. So some external agency is used, or the work is being done by an external agency, which is against this gravitational force, and that external agency's work done is nothing but called as mgh, which is nothing but stored as potential energy. Okay, so basically our ball has some capacity. That capacity is called here as potential energy. In other terms, it can be said as some external agency which is doing the work against the gravitational force. Okay, so that's how we can understand more about this potential energy concept. Okay, so now let us understand some of the mathematical formulations of it and then move forward. Okay, so first of all, gravitational potential energy of an object. So what can be understood from this 4 words given? So first of all, it is written of what? Potential energy of an object. Okay, so potential energy is basically can be understood as something or an energy which is stored inside it. Okay, if it is written as gravitational potential energy, that means the potential energy due to the force F, right, or due to an external agency which opposes this force of gravitation is called as gravitational potential energy. Okay, so gravitational potential energy of an object as a function of height h is denoted as Vr. Okay, and it is the negative of the work done by the gravitational force in raising the object to that height. Okay, So I hope it is clear. So why it is given as negative? Let us see here. Okay. Let us look. So what is the direction of displacement? So this was the direction of displacement of the ball. So it was generally at the ground, and then we kept it at this location. Okay. And what is the direction of gravity? Gravity direction is in this direction. So therefore the work done would have come out equal to nothing but mg into h into -1. Correct? Because the direction of the displacement and force is in another direction. But here, how we are defining the potential energy? Potential energy is a negative of the work done by the gravitational force and raising up to the time. So this will be minus mgh into -1, and hence this is equal to nothing but mgh. Okay. So I hope this line is clear. Therefore, we got that potential energy can be written as nothing but equal to mgh, or gravitational potential energy written as equal to mgh. Okay. Fine. Now, if h is taken as a variable, it is easily seen that the gravitational force F equals what? It equals a negative of the derivative of v of h with respect to h. Okay. So what they're basically doing, they are just trying to find out the value of, so it is nothing but, we know v of h is nothing but equal to f into h basically, correct? So if we need to calculate the value of force, then what we can do basically, we can just write f is nothing but equal to v by h, right? In differential form, we can write this is nothing but equal to negative of d by dh. Okay, please understand why we are understanding here this is negative, because we understood this complete concept as something or an external agency. Please remember, this is a very important concept. We understood this complete thing as an external agency doing against the gravitational force or against something. So that is why, because we are doing the work against, so in the actual concept definition, we have already put a negative sign. Our answer is opposite of that. That is again a negative sign. That's why we are adding a negative sign. So I hope it is clear, because the work done by an external agency, and we need to calculate the work done by a force. That force will be negative of the work done by the external agency. Okay. Fine. So therefore, it can be easily seen that the work gravitational force F equals the negative of the derivative of v of h with respect to h. Then what we can write? We can write F is nothing but equal to minus d by dh into v of h, which is equal to minus mg. So the negative sign indicates that the gravitational force is downwards. So what does this negative sign says? It simply says that the gravitational force is downwards. Okay, so quite evident. You know, whatever sign convention is, the above sign is positive, and if it is going downward, then it is negative. Okay, so because acceleration is being acted downwards, so therefore gravity, if it's a negative, then that means you are going in the correct direction as far as your convention of sign convention are being understood. That thing being said, now when released, the ball comes down with an increasing speed. Quite evident. Now, if we try to release the ball from this location here, what is happening? We know in free fall we have understood the concept of free fall when we are trying to understand the chapter motion in a plane. So basically what is happening with the increase in time, the amount of velocities keep on increasing, correct? The ball comes with an increasing speed just before it hits the ground. Its speed is given by the kinematic relation v square is equal to 2gh. Okay, so how can we arrive at this relation here? So we can directly use simple kinematics equation. So we know what, that let us say there is one object which was kept at a displacement of, let's say, h, okay, with an acceleration in this direction g. Okay, so we can use the relation v square is equal to u square plus 2as, correct? Now what we can write here, we know that the initial velocity was 0, so and this will be 0. So v square is nothing but equal to 2 multiplied by the value of minus g into displacement, which is also negative direction, which is minus. Okay, so I hope it is clear why I'm putting minus g and minus s, because both are in the downward direction, and the downward direction sign convention say that everything which you measure in the downward direction will be taken as negative. So this is nothing but equal to v square, which is equal to 2gs. Okay, or in this term you can take this as nothing but equal to v square, which is equal to 2gh. Okay, so this is not even written h here. Let me solve this and say. Okay, so I hope it is clear that v square we got at that answer is equal to nothing but 2gh. Fine. That thing being said, let us move forward. Now, so so we got a kinematics relation as v square is equal to 2gh, correct? It's 2gh. Now let us try to do some of the mathematical manipulations here. So first of all, let me put 2 in this side. So I will get v square by 2 is nothing but equal to gh. So there is no harm in the equation. Now let me multiply m on both sides. So if I multiply m on both sides, I get mv square by 2 is nothing but equal to mgh. Okay, so if you look at this line, this carefully, it is nothing but the formula for kinetic energy. And if you look at this very carefully, you will get this. This is nothing but your potential energy. Okay, so what is the final conclusion here? So this equation can be written as nothing but half mv square, which is equal to mgh. What does it show? It shows that the gravitational potential energy. What is gravitational potential energy? This is your gravitational potential energy of the object at height h. Of the object at height h when the object is released. So when we are, let us say we are doing a free fall of this object from this location. So the gravitational potential energy of the object at height h when the object released manifests itself as kinetic energy, or in easy terms you can say converts potential energy into kinetic energy of the object on reaching the ground. So therefore what we can say that when it reaches the ground, it will have some velocity, and hence this potential energy is converted completely into kinetic energy. Fine. That's how you can understand this line here, that is half mv square is nothing but equal to mgh. Okay, please remember this part of the explanation is done when we were at higher location, and this part of explanation is done when we were at the lowest location. Okay, so even the low location is not same. Okay, fine. Next thing is physically the notion of potential energy is applicable only to the class of forces where work done against the force gets stored up as energy. This is a very important line, that we can use potential energy only and only where we can only use in those class of forces, or we can find the potential energy of, let's say, some force F only and only when the work done against the force gets stored up. So if there is a way in which the body can store up that energy, then and only then we can use the concept of potential energy, otherwise we cannot. Okay, fine. The next thing is, when the external constraints are removed, it manifests itself as kinetic energy. So basically we are saying that when we remove this all gravitational force, basically we allow it to free fall, and finally what happens is that this completely stored energy is being converted into potential, is being converted into kinetic energy. Okay, fine. Next thing is mathematically for simplicity in one dimension. So if you remember correctly, we started this complete discussion with understanding of this complete concept as one in one dimension. Okay, so mathematically for simplicity in one dimension, the potential energy V of x is defined if the force F of x can be written as this. Okay, so as in previous case scenario, here also F was calculated as equal to minus dV by dH. So in similar case scenarios, in only in terms of H, they have substituted as X. So I can write that force, that variable force, is nothing but equal to minus dV by dx. Okay, so I can just calculate this and calculate the value of force. Okay, so therefore the mathematically for simplicity in one dimension, the potential energy, that is V of x, is defined if the force F of x can be written as nothing but F of x is nothing but equal to minus dV by dx. Okay, so I hope the concept of potential energy, the change of potential energy into kinetic energy, understanding that potential energy can only be produced only for those forces which can store the energy, and finally we also got that this variable force can be calculated using the potential energy by using the formula, that is F of x is nothing but equal to minus dV by dx. Okay, fine. That thing being said, let us understand more about this, and let's end this discussion after this slide. Okay. This implies what? Okay, so we know what is this f of x nothing but equal to minus dv by dx. So you can use this relation here to find out that is f of x dx is nothing but equal to integration of dv, that's in minus sense, okay, xi to xf, nothing but initial minus final. Please remember it is not final minus initial because there was a negative sign being involved there. That's why it's initial minus final. So initial minus final change in potential energy is nothing but equal to the work done for moving from xi to x. Okay. So this implies that integration of xi to xf f of x dx is nothing but equal to integration vi to vf dv, which is equal to vi minus vf. Okay. Therefore, the work done by a conservative force such as gravity depends on the initial and the final positions only. Okay. So then a new word has come up here that is called as conservative force. So before understanding the line here, let us first understand what is a conservative force. So I have just written the conservative force definition directly here. So conservative force is a force with the property that the total work done in moving a particle between the 2 points is independent of the path taken. So what does basically mean? Let us suppose there was an object at this location. It moved to this location. Okay. So either the path was this, either the path was this, either the path was this. Okay, so in each of these sequences, we only use this complete displacement and calculated the value of force, or basically calculate the value of work done. Okay. You may arrive at a situation, okay, you may ask a question that, but for work done is always depending on displacement only, it doesn't depend on path length. That is correct. But what actually happens between a difference between the conservative force and non-conservative forces? In the non-conservative forces, there is a generally leakage of the energy happening. That is basically there is a reduction in the final energy. So because reduction in the final energy, what happens is if we go in a complete loop, then the amount of work done which we get at the final value is less than the initial energy. Why it is that the case? Because there is some dissipation happening. So that is the basic crux. So that is the basic difference between conservative and non-conservative force. But in more general sense, we will try to explain the situation. We say that the total work done for moving the particle between 2 points is independent of the path taken. Because what is generally happening is either any path you take, there is no dissipation happening. There is no dissipation happening. So hence we can directly use the displacement concept and calculate the result. So that is the basic crux of using understanding or making example of conservative force. Okay, that is the basic meaning of why we use the concept of independency of path. Okay. Fine. So let's move forward. So this implies that, so what we got that nothing but Vi minus Vf. So please remember it's not Vf minus Vi here, it's Vi minus Vf here. That is equal to integration of xi to xf f of x dx. Okay, so that's how we do this potential difference. Therefore, the work done by a conservative force. Now let us understand the second line. So the second line says that the work done by a conservative force, examples are given. What are the examples of conservative force? Such as gravity. Depends on what? It depends on the initial and the final positions only. Quite evident because it is independent of the path. Okay. Next thing is let us understand an example involving inclined planes. Okay, so what is basically an inclined plane? This is an inclined. Okay. So if an object of mass m, let us say we have object of mass m kept here, okay, is released from rest on the top of a smooth frictionless inclined plane. So let us say the mass was being kept here only. Okay, and it is released from rest from the top of a smooth frictionless inclined plane of height h. So this was the height h. Its speed at the bottom will be under root 2gh only. So what is the basic meaning? What we have basically done, we just did mv square is nothing but equal to mgh. So getting cancelled, we got v is nothing but equal to under root 2gh. Okay, so this is only and only possible. First of all, why? Because only gravitational force is acting, and second thing is because it is written as frictionless. That means there is no dissipative force or no non-conservative force acting in this direction. Okay. So that thing being said, next thing is so that is the basic explanation of why we we will get another 2gh only, irrespective of angle of inclination. So this angle doesn't make any difference whenever we try to do it, but the only catch is that the plane here should be smooth or frictionless. So only and only force which is acting here should be your what we can say. The only and only force which is acting here is gravitational. Fine. So that was the basic explanation of conservative force here. So moving on. So thus at the bottom of the inclined fluid it acquires a kinetic energy which is mgh. So basically half mv square is in the downward portion and in the top portion it was mg. Okay. So if the work done or the kinetic energy did depend on other factors such as velocity or the particular part taken by the object, the force will be non-conservative. So the non-conservative definition is written here. So let us say that the work done or the kinetic energy depends on what? It depends on factors such as velocity or the particular path. It depends on particular path also. Then the force would be called as a non-conservative. Okay. Next is the dimension of potential energy. So let us calculate the dimension of potential energy here first of all. So it is nothing but, we know it's nothing but m into g into h. So what is m? M is nothing but kg. What is g? G is nothing but your meter per second square. And what is h? H is basically meters. Okay. So if I calculate the value of dimension of this in terms of mlt, I will write it as m1. Length will be 2 here and time will be -2. So if you see clearly, if you remember correctly, this was the same which we obtained for kinetic energy also. And that is how we can use kinetic energy is equal to potential energy. Okay. Okay. The dimensions of potential energy are m L2 T minus 2 and the unit is joules, which is the same as the kinetic energy order. Okay. So that thing being said, let me stop the discussion here only. We will start the discussion from this point slide in the next one. Okay. So let me stop it here. For the course progress for you, we started with the introduction. We have completed the concept of work energy theorem. We have completed work, that is force into displacement. We have completed kinetic energy. We have completed work done by variable force, that is basically the area under the curve of f of a, f and x. And we have completed work in this theorem for a variable force also, that is integration of kf, from ki to kx, dk, basically that is kf minus kx nothing but equal to integration of kf minus k nothing but equal to integration of xi to xf f dot dx. Correct? And we understood the concept of potential energy correctly. Currently we are on this topic. After this topic is completed, we will move on to one of the major topics which are the building blocks of everything which we will study in the future, such as let's say nuclear energy, or let's say anything regarding charges, current, electricity, anything which you study about energy. Always this rule or this law is being followed. That is the conservation of mechanical energy. You will understand this, you will understand more about the spring, etc. in the subsequent classes. So for now, let me stop it here only. We will discuss more about this in the subsequent classes. So let me stop it here. So thank you so much.